Welcome to The Explainer. Today, we are diving into something that sounds like it's straight out of a sci-fi movie, but it's grounded in some of the most fascinating physics out there. We're talking about quantum radar.
So, let's just start with this. A huge challenge that has been driving military tech for, well, decades. How do you see something that is literally designed to be invisible? Whether it's a stealth bomber trying to sneak past your defenses, or an enemy flooding the airwaves with noise to blind you. The goal is always the same: stay hidden. But what if there was a completely new way to look?
And that right there, that's the whole problem that quantum radar is trying to solve. See, for all its power, conventional radar is basically stuck in this endless game of cat and mouse with stuff designed to beat it. And it's a game that it doesn't always win.
Okay, so think about regular radar like this. You shout into a canyon and wait for the echo. Super simple, right? It sends out a big pulse of radio waves. Well, stealth tech, that's like shaping the canyon walls so your shout bounces away from you so you never hear the echo. And jamming, that's like having 100 other people screaming at the top of their lungs right next to you, completely drowning out your tiny echo. Either way, the thing you're looking for might as well be invisible.
But what if you could just completely change the rules of the game? I mean, instead of just shouting louder, what if you could whisper and still be able to pick out your specific whisper from inside a hurricane of noise? Well, that's the massive leap that quantum physics is promising.
So instead of just blasting out a huge amount of energy and, crossing your fingers hoping you hear something back, quantum radar uses this genuinely mind-bending property of physics called quantum entanglement. It's all about using the weird, spooky, linked nature of these tiny particles to do things that normal radar just can't.
The promise here is, well, it's a system so incredibly sensitive that it can find its own little reflected signal even if it's buried under an absolute avalanche of noise. See, it's not about being louder, it's about having a secret handshake with the particles you send out, so you know them instantly when they come back, no matter how faint they are.
Okay, so how in the world does this secret handshake actually work? The physics behind it can get, well, pretty intense, but the core idea is actually beautiful. It's all based on a process called quantum illumination.
All right, so it all kicks off by creating these pairs of linked particles, entangled photons. Just think of them as quantum twins. And here's the crazy part. No matter how far apart they get, they're still connected in this really special way. So one of these twins, we call it the idler beam, is kept safe and sound at the radar station. Its brother, the signal beam, gets sent out to actually go look for the target.
And this right here is the absolute heart of it. Because those two beams are entangled, the system back home holds the key. It has a perfect blueprint of the particle it sent out. So it's not just listening for any old echo. Nope. It's waiting for the one specific particle that fits its quantum lock. So when that super faint signal comes back from the target, it gets compared to the twin that stayed behind. And if they share that unique quantum connection, bam, the system knows it's a real detection. Everything else, all the other signals, enemy jamming, background noise, whatever, they don't have that special link. So they just get tossed out. They're just noise.
Okay, so this sounds completely unbeatable, right? Like a total game changer. And in theory, it is. And this is a big but, in the real world, the gap between this amazing idea and a piece of gear you can actually use is, well, it's gigantic.
So, let me ask you, what do you think the current operational range is for these experimental quantum radars? Hundreds of kilometers? Maybe dozens? Nope, it's 1 meter. 1. That's the reality check. We are a long way from tracking a stealth fighter with this stuff.
And the reasons why? Well, they happen to be some of the toughest problems in all of quantum engineering. First up, you've got something called quantum decoherence. Basically, that super fragile quantum twin connection, it breaks really easily. Like just bumping into air molecules can shatter it. Then there's the quantum memory problem. You have to store that idler beam perfectly while its twin is off on its trip, and that technology is still deep in the lab. Put it all together and you get a very limited theoretical range and a super narrow focus. You can basically only look at one tiny spot at a time.
So, where does that leave us? Is this whole quantum radar thing fact or fiction? Well, to figure that out, we really need to cut through the media hype and look at where this technology is realistically going.
You see these headlines screaming about a super radar that's going to make billion-dollar stealth jets completely obsolete. But the actual science? It's pointing somewhere totally different. And honestly, maybe even more interesting. The reality is, the first actual uses for this technology probably won't be long-range military stuff at all. It's going to be for super sensitive, very short-range things.
And this is where the story gets really cool. Think about it. That same incredible sensitivity, that ability to see the tiniest details with almost no power. What does that sound perfect for? Looking inside the most delicate thing we know, the human body. Forget tracking jets for a minute. Imagine using this for incredibly detailed, completely safe biological scans. Now that would be a revolution and has nothing to do with the battlefield.
And that's really the big question we're left with, isn't it? Is quantum radar going to change the future of warfare someday, or will its true revolution be in medicine? Will its amazing ability to see the unseen actually end up helping us better understand ourselves? We'll have to wait and see.